Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to explain what is pulse width modulation, commonly referred to as PWM, and what are its applications in electronic systems. I shall lay down MSP430 G2231 PWM parametric tables for you so you can write your next PWM software with confidence. Let's get started. I have written a software for demonstration purposes for MSP430 G2231, cycling the PWM digital waveform up and down. The idea is to illustrate what PWM is by capturing it on an oscilloscope screen. MSP430 microcontroller is programmed to generate a digital waveform in an endless loop and captured by the oscilloscope. It is like any digital sequence except the variable on and off time while keeping the frequency same. This variation in on-off times impacts the equivalent output DC value of the PWM signal, a concept used widely in electronics and closed-loop control systems. By varying the duty cycle, efficient feedback control can be implemented in closed-loop systems. A major parameter for PWM is duty cycle, which would define the PWM output. For a 5 volts digital waveform, a 0% duty cycle means 0 volts on output and 100% means 5 volts output. A 50% duty cycle means 2.5 volts. Usually, the PWM frequency is fixed for an operation. Frequencies do not directly impact the output equivalent voltage, but influence it indirectly in terms of efficiency and system noise. This is a screen capture of a mini oscilloscope sitting on my desk. The PWM frequency is 1 kHz and duty cycle is 10%. It is only 10% on and 90% off. A good example of PWM is DC motor control. DC motor speed is commonly controlled by PWM inputs to the control modules. Higher the duty cycle, higher the speed is. A perfect use case is common drone systems. They use brushless DC motors, and motor speed is controlled by electronics controllers, which have PWM inputs, and duty cycle of PWM is proportional to the throttle input. Now we shall look at the PWM parametric tables for MSP430 G2231 microcontrollers. Timer A CCR0 and CCR1 are two main registers which shall control the PWM frequency and duty cycle. This table describes some of the PWM parameter sets for a clock of 1 MHz. Following the basic formulas for PWM frequency and duty cycle, let's take example of CCR0 as 1000, which means PWM frequency of 1 kHz, and CCR1 value of 250 means 25% duty cycle. Similarly, for CCR0 value of 2000, PWM frequency is 500 Hz and CCR1 value of 500 also comes out to be 25% duty cycle. Timer A, TA0CTL, is the control register for Timer A. This register will configure the desired functionality for Timer A. This table describes some of the possible bit definitions. For my particular case, I am going to select the TASSEL2, which sources the clock from 1 MHz DCO clock, and MC2, which is continuous count mode. Let's look at the source code in a bit more detail, and it is compiled and downloaded via Code Composer IDE. Clock section sets the clock to 1 MHz. Port selection has been set as port 1 pin 2 as discussed earlier. PWM configuration has been set in PWM parametric section, 1000 Hz frequency and 50% duty cycle initially. In last, Timer A control register has been set up as discussed earlier. The PWM test rig has MSP430 Launchpad with Code Composer Studio and port 1 pin 2 as output connected to the oscilloscope, recorded by CAM. Current PWM config is 1000 Hz and 50% duty cycle. I am going to change the config as CCR1 to 250, 25% duty cycle, compile and download the code and observe the impact. Code compiled and downloaded and the configuration has taken effect. You can observe that PWM frequency has not changed. It remains 1000 Hz, however, duty cycle is now 25%. In another modification of parameters, I am going to change the duty cycle to 50% with new PWM frequency of 500 Hz, CCR0 to 2000 and CCR1 as 500. Let's compile and download. It can be seen that frequency and duty cycle has been updated accordingly. You can use the parametric table published earlier to test and try new PWM configurations.